Welcome to Everyday Mathematics. Today we move forward to quarterfinals number 4 of the 2026 MIT Integration Bee. We had three problems rather, 1, 2, and 3 are shown here. And so yeah, please stay put and see how we may be able to solve these problems. So problem number 1, the definite integral from x goes to 1 to x to infinity of 1 over the square of the floor function of x times the ceiling of x. So I guess the first thing we need to do is to define for ourselves what the floor function is and what the ceiling function is. So the floor function of x equals to integer k if x is less than k plus 1 or greater or equal to k. Okay, and the ceiling of x equals to k plus 1 when x is less or equal to k plus 1 and greater than k. Okay, so this is important for us. And what does that mean? It means that now we have these discrete regions, right? From k equals to 1 to k equals to infinity. And in each, we can now integrate 1 over x squared become a floor function become k squared, and ceiling function x squared becomes k plus 1 squared. So these are constants. We can pull these out. So we have 1 over k squared, k plus 1 squared, and which means that we have and so here we see k plus 1 minus k means that this becomes 1. So what now becomes our problem is the summation from k equals to 1 to infinity of k squared times k plus 1 squared. So which is pretty tractable, because now we do have this summation, right? And the important thing for us to note is what we call the Bezier problem. You can Google that out, and that says that the summation from k equals to 1 to infinity of 1 over k squared is equals to pi squared over 6. So this is what we're going to use for this problem. Okay, so going back to our problem here, we do have the summation from k equals to 1 of infinity. I have k times k plus 1 squared, which can be represented as 1 over k minus 1 over k plus 1 squared, right? So which is 1 over k squared minus 2 over k times k plus 1 plus 1 over k plus 1 squared. Now we can split this out further, and that means that we have 1 over k squared minus 2, 1 over k minus 1 over k plus 1 plus 1 over k plus 1 squared. Okay, so that pretty decent. So we have now summation from k equals to 1 to infinity of 1 over k squared minus 2, 1 over k plus 1 over k plus 1 plus 1 over k plus 1 squared. Okay, so we can take this independently. 1 over k squared minus twice summation from k equals to 1 to infinity of 1 over k minus 1 over k plus 1 plus summation from k equals to 1 to infinity of 1 over k plus 1 squared. Okay, and as we can see, this one here already is pi squared over 6, but here, since from k equals to 1, it means we have 1 over 2 squared, so we're missing 1. So this essentially is pi squared over 6 minus 1, right? And this one here is important because it's like having 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3. And you begin to see that the succeeding values cancel, and so this part becomes 1. The remainder is just 1. So 1 times 2 is negative 2. Negative 2 here times this negative plus this negative 1, it becomes negative 3. And this plus this is pi squared over 3. So we have pi squared over 3 minus 3, which is equals to pi squared minus 9 over 3. So in other words, our integral from x equals to 1 to infinity, or 1 over the floor function of x squared times the ceiling of x squared equals to pi squared minus 9 over 3. And that, ladies and gentlemen, is our answer. So problem number 2, the definite integral from x equals to 0 to x equals to infinity of 4 cosine 4x over x to the power 4 plus 4. So this is certainly interesting. One thing we may want to do is express using Euler's identity. We know that cosine of x is equal to e to the power ix plus e to the power over 2, where I is the imaginary unit. Now that's root negative 1. So our integral now becomes 0 to infinity. And then we have this 4 here. So we say 4 over 2, talking about this 2 here. And then we have e to the power I 4x plus e negative I 4x divided by x to the 4th plus 1. Okay, and then x to the power 4 plus 4 is the same as x squared minus 2x plus 2, x squared plus 2x plus 2. So we can now re-express, since this 4 divided by 2 is going to be 2, we can now re-express our integral in form of partial fractions. So we can have e 4x plus and we have 1 over 8 up there, but we have x plus 2 over x squared minus 2x plus 2 plus x plus 2 over x squared plus 2x plus 2. Okay. So this becomes 1, becomes 4, and then we can proceed and say that so we have a quarter, 0 infinity, plus 2 plus x plus 2 . So it's very easy to realize that this part here quickly becomes, when we flip, it's actually symmetrical. This integral is symmetrical about x equals to 0. If we factor the negative parts and then we look at the positive x parts, this essentially leads us to just an integral of from x equals negative infinity to infinity of e for x negative x plus 2 over x right, because when x is negative, this part here shifts to this and this part shifts to this, and then we realize that this part becomes same as that. So that is the case. So we can now rearrange our integral. This is same as x minus 1 squared plus 1 plus x plus 2 over x plus 1 squared plus 1, like that. Which is great. We can look at this part here. This let's just maybe rewrite this into 2. Our integral now is a quarter, infinity to infinity, of negative x plus 2 over x minus 1 squared plus 1 e for x plus 2 x plus 1 squared plus 1. So we could say in this situation, let u be equal to x minus 1 such that du dx equals to 1, and so du is equals to dx. Okay, so the first term of the integral becomes, we can pull the negative out so that we have u minus 1 e negative 4, and we have u plus 1 here over u squared plus 1 du. And we can say let p, in this situation, let p be equal to x plus 1 such that dp dx is equals to 1, and so dp would be equal to dx. And so we have integral negative infinity, and we have a quarter here. Okay, so we have p plus 1 e negative I to the power e to the power I for p minus 1 over p squared plus 1 dp, such that we can pull the constant here, negative, and we have I4 out, negative u minus 1 ei4u over u squared plus 1 du plus a quarter, and then we have e negative I4, this and this, and negative infinity, we have p plus 1 ei 4p over p squared plus 1. Now we can take everything back into the x domain, so that we have negative a quarter e I to the 4 infinity, and we have x minus 1 ei 4x over x squared plus 1 dx plus negative 4 x plus 1 e 4x x squared plus 1 dx. Let's collect like terms. So we here can have negative a quarter e4 negative I x I for x over x squared plus 1 plus positive a quarter, because of this negative 1 here, we have I4 plus I negative I4 okay. Now since sine x is equals to I e to the ix minus over 2I, this here now becomes negative a half I sine 4 x over x squared plus 1 dx plus this here is cosine, actually it's a half, so we'll just delete that and say a half cosine of 4 rather ei for x over x squared plus 1 dx. Okay, and here I was trying to avoid contour integrals here, but I guess there's no way about it. So we have negative a half I sine 4, and we could say z. Let's express everything in a complex format. So I for z over z squared plus 1 dz plus a half cosine of 4 eiz over z squared plus 1 dz. And we can use the residual technique, where first we can express the denominator as z minus I, z plus I, diz, we have z minus I, z plus I, dz. And so this integral could be expressed as negative sine 4 residual of our function, the integrand, with I times 2 pi I plus a half cosine of 4 residual. Let's take the integrand as g I times 2 pi I. So residual of fi would be equal to limit as z tends to infinity of z minus I times z e I for z over z minus I z plus I. So at that point of singularity, what do we see here? So this is so just go and we have I e I for I over 2I cancel, so we're getting e to the power negative 4. And what about res of gi? That's the same as limit z tending to infinity of z minus I e to the power I for z over z minus I times z plus I, which actually there's a half here. We forgot that. So this here is the same as e to the power negative 4 over 2I. Okay, so since our answer is supposed to now be negative a half I sine 4 times the res of fi 2 pi I plus a half cosine of 4 residual of gi 2 pi I. This is negative a quarter, negative a half rather, I sine of 4 times e to the power negative 4 over 2 times 2 pi I to cancel. This I and this I interact to make negative 1, and here we have e to the power negative 4 over 2I times 2 pi I. We have this and that interacting, this and that interacting. And so since this and this become negative 1, this negative 1 gets cancelled, so we have essentially a half pi e negative 4, and we have sine of 4 plus cosine of 4 as our answer. So in other words, the integral from 0 to infinity of 4 cosine of 4x over x to the 4th plus 4 equals to pi over 2 times e to the power negative 4 times sine of 4 plus cosine of 4. It's a kind of a very strange answer, and I don't know how one would have been able to work this problem out within the short time. But I'm also certain you could have tried to work with the residuals earlier on than we did attempt to do it. So until next time, if you have any question, please reach out to us. We're going to move to the last problem, and then we'll end this video here today. Finally, problem number 3. The sine of arc cosh of x integrated indefinitely. I think I would want to substitute for this. I would say let u be equal to arc cosh of x such that cosh of u is equals to x. And that what that means is sinh u du dx equals to 1, meaning that sinh u du would be used to substitute for dx. Okay, and what do we do next? So we'll say, okay, we have sine of u, sinh of u du, which can be expressed as sine of u, the derivative of cosh of u du. And so we can use integration by parts, which tells us that if you are integrating a product of two functions where one is v and the one is the derivative of function capital U, we have a product of uv minus u dv. In this scenario, our v is sine u, our u is cosh of u. Okay, so we have sine of u, derivative of cosh of u would be equal to sine of u cosh of u minus we have cosh of u derivative of sine of u. So this becomes, we have sine of u cosh of u minus cosh u cosine of u. Okay, we can have a nested situation here. Well, we can say that this is sine of u cosh of u minus cosh of cosine of u rather times the derivative of sinh of u. Okay, so if we have sine of u cosh of u minus cos of u times the derivative of sinh of u, this means that we have sine of u cosh of u, let's just put brackets all over the place, minus cosine of u sinh of u minus sinh of u times the derivative of cosine of u. So this is sine of u, cos of u, minus cos of u, sinh of u, minus, this is negative sine, so it becomes sine of u, sinh of u. And this here becomes the same integral we have on the left hand side. So we bring it back here, we have 2I equals to sinh of u cos of u minus cos of u sinh of u. So since we have 2I is equals to sine of u cos of u minus cosine of u sinh of u, means I is equals to a half sine of u cos of u minus cosine of u sinh of u, obviously plus the integration constant. We had said that u equals to arc cosine of x, and rather cosine of u is equals to x, sine of u is equals to the square root of, since cosine, cos rather, cos, and so sinh of u would be, since cos squared u minus sinh squared u is equals to 1, and so here we'll have 1 plus s. Maybe we can just rewrite everything here and make it clear. So we have cos square of x minus sinh square of x equals to 1, which means that sinh square of x equals to 1 cos squared x minus 1 and so since we said our integral equals to sine u cos u minus cos u sinh u, and we saw that u equals to arc cos of x, such that cos of u equals to x, sinh u would be equal to square root of x squared minus 1. So our integral sine of arc cos of x would be equal to sine of u, which is arc cos of x. Cos u is x, so we put x there, minus cos u would be cos of arc cosh of x, since u is square root of x squared minus 1. Obviously plus the integration constant there. So maybe, yeah, let's rewrite it a little bit more neatly. X sine arc cosh of x minus square root of x squared minus 1 cosine of arc cosh of x plus c. And that is the answer, ladies and gentlemen. So yeah, thank you very much for tuning in. It was an absolute pleasure going through some of these problems. If you have any question, please don't hesitate to reach out to us. I would always love to explain some of the things to you. Until next time, bye-bye.